On mute.
Welcome to another GeogPod, Geographers. I am Mr. Hattel and Mr. Unite is here with me. Say hello, sir.
Hello, hello.
And today we are going to do another GeogPod for you, and the focus of this one is on changing climate. So without further ado, let's get started, and I'm going to zoom in for you to each of the little sections we are looking at. I'm going to start with a very simple question. What is climate change? And the key thing to remember about climate change is that it is large scale and long term in shifting the patterns of weather and therefore climate over a long period. So we're talking about temperatures changing and weather patterns changing over hundreds of years here. And then if we think about our time period and where we are in the world's history, we are today in what's currently called the Quaternary period. Now, the Quaternary period is actually split into two parts, and our current epoch or period is actually called the Holocene epoch. Now, the Quaternary period as a large time period is the last 2.6 million years. During this time, temperatures have always fluctuated, and if you have a look at the graph on the right here, we can see that temperatures were low in the initial Quaternary period, so they were down -3, -0.3 or -0.4 below zero. But you can actually see that more recently, since the 1960s mainly, we have seen a rise, although still fluctuations, a rise in temperatures in the Quaternary period. So there are essentially warm spikes and cold spikes. And you could refer to these spikes above and below zero as glacial and interglacial periods. The glacial ones, the glacial periods of time, are where ice is forming, and that is where the temperature dips below that 0 degree threshold. And the interglacial periods are when the temperature rises above zero, and so glaciers start to melt. And actually, I'm going to hand straight over to Mr. Unite on that, so he can talk to you a bit about the evidence we have for that.
Thank you, sir. So what we can really look at is this particular graph that you're looking at covers the last couple of 100 years, and that really shows you, when we talk about this later, about the impact of like the enhanced greenhouse effect, global warming as you know it. But there's some really good examples in further history back from that, where we look at something called the Little Ice Age, as well as something called the Medieval Warm Period. So the Little Ice Age is a really good example of a glacial period, and again you can see it sort of finished about 1870, which is just before the start of that graph above. But the key thing about this is this was just an example of that glacial period, where we started to see obviously growing glacial areas on the Earth and increasing sort of size of glaciers, Arctic sea ice, that sort of thing. So with that will come some impact. Okay, so obviously we can see, as you can read from 1, 2, and 3, that the sea ice would engulf places like Iceland, and therefore it would grow in size. Places like the River Thames, you can see pictures. You can still see pictures of this if you were to Google this particular event. You'll see pictures and sketches of people skating and stuff like that on the River Thames. So it's been recorded in history like that. So a nice little link that we know about this Little Ice Age, not necessarily because we were there, but because people left diaries and people left photos of it. So that's a nice little link to one later. But also, not long before that, a couple of 100 years before, there was also another period, which was an interglacial, where there was a warm period. It was called the Medieval Warm Period. And again, it was just slightly warmer. So this just shows, as Mr. Hatcher has described, that we do go through natural fluctuations. But in particular, for those last couple of 100 years, as the graph shows above, if you do the line of best fit, we can see that it's continually growing. So, well, as I've alluded to there, we can have some forms of evidence for climate change. So if I hand back over to you, what else can you tell me about evidence for climate change and how we might pick that out?
Yeah, thank you, sir. So there are 4 main categories to think about in terms of evidence for climate change. And these 4 main categories actually cover hundreds of years, if not millions of years back. All right, so you can see on screen here, we've got geological fossil evidence, ocean sediment evidence, ice core evidence, and historical records. So we are talking here about evidence in history. So it's not very recent. It goes back potentially millions of years in some cases. And what you essentially need to know for these 4 categories is how reliable they are. So you really need to think here about how reliable each of these pieces of evidence are. So I'm going to go through all 4 now very briefly and give you a summary of what they tell us. So geological fossil evidence. This is plants and animals, or fossils, which remain on the landscape in certain parts of the world. Now, the key thing about this is we find fossils like historic plants and animals in places where those plants or animals would not live today. And the reason they would not live there today is because the environment or the climate would not match that animal or plant's conditions or needs. So that tells us that the climate in that area where the fossil or plant is found has actually changed. And actually, it no longer suits that plant or animal if they were alive today. So that suggests that there were periods of warmer or colder times in that place hundreds of thousands or millions of years ago. So that is geological fossil evidence. And we've got ocean sediment evidence. Now, in oceans, sediment builds up over time. And actually, this relates back to your distinctive landscape topic. Okay. So we have layers and layers of different sediment of rock building up over time. When those layers build up, oxygen and other substances like carbon dioxide is actually trapped in those layers of sediment. Now, what we can do is scientists can analyze those layers of evidence, and we can use them to calculate what the atmospheric temperature was at the time that the layers were created. And therefore, we can also look at how the atmospheric temperatures have changed over that time period compared to today. So if we analyze, therefore, ocean sediment layers, we can actually see how temperature has changed over time. We then have ice cores. This is one of the biggest ways in which we today look at the temperature change and climate change over the last few million years. So ice cores, of course, are within ice sheets and ice caps. It involves drilling deep down into the ice sheets or caps, particularly in the Arctic or Antarctica today, to look at the levels of molecules or carbon dioxide held inside the ice through ice bubbles over a long period. So if we explore these ice cores, what we can actually find is the levels of carbon dioxide, or the levels of bubbles, if you like, within the ice throughout time, the deeper we go down into the ice. And that can tell us about fluctuating temperatures in history. And that also then means we can decide what was happening to the climate over time through looking at that ice core. That is quite a reliable piece of evidence for climate change and temperature change. And then finally, we've got historical records. Now, you can refer to historical records as mainly being subjective or opinion-based records. And that's because they are mainly things like ancient cave paintings, diaries, written observations, and images. And these are taken through personal accounts. So someone in history drew a picture of the landscape they could see, or wrote a diary extract about a particular weather event that was taking place. And so we have to take these ones with a pinch of salt. They're not as reliable because they are based on someone's opinion. And for example, if Mr. Unite was to describe the weather today that we've got outside, and I was also to describe it, they are two different opinions. So there may be variations in what we decide the weather is like today. So key thing for all of this evidence for climate change is to really question how reliable it is, what might not be so reliable, and be able to evaluate which is best and which is not, and why. Mr. Unite, any questions?
No, smash that. So I really like that. Some good summaries. Like the fact you mentioned about the subjective, that links very nicely into our fieldwork discussions, as well. So no, really good.
So I'm going to hand over to you for recent evidence. So this is in the last 100 years.
Super, thank you, sir. So what's really good here is obviously we think about the ones that Mr. Hatcher has talked about. They give us a really good breadth of understanding. We can go back in a long way into the past to find out evidence. But obviously, the more recent evidence with technological advances, even in the last decades, technology is so much better than what it was, 50, 60 years ago. So we can really find that the data we're getting now is really good. But obviously, it's a lot more short term. So there's three main ones that we might look at. Okay, so for one, global temperature data. Well, if you think about opening up your phone, a BBC News app, you can get data for the weather for the local area you're in, what it's predicted to be, and all of that sort of thing. You can see what's going to be in a week, what it was like a week ago. Well, all that data can be collected and give us global temperature data for the entire year, so give us averages, and therefore get really accurate records of what the weather was like on every single day at time changes, so we can see it. I'm sure you've probably heard, of people saying, oh, this is the hottest summer that we've had for X amount of years. Well, that's the sort of thing about where we get that data from. In terms of ice sheets and glaciers, again, these are really useful because we can use satellites. We can use literally someone can walk up to a glacier, take a picture of it and see how far it is either retreating or growing each time. Okay, so again, we can figuratively see what's happened. So for us, a really common one, you've definitely seen this on the news. I've used this with my year 10s reasonably recently, where they've seen pictures of Arctic sea ice satellites and how it's been declining and what happens to it in the summer and the winter and that sort of stuff. We've also been keeping an eye on the news as well. There's also bits where, big ice shelves are breaking off in the Antarctic and those things. So you've probably seen those elements out there. But again, that growth and decline of ice sheets and glaciers are really important, because if we're in a period of cooling, like that glacial period we mentioned earlier, it's going to be growing. It's going to be evidence that there is a cooling period. And last but not least, obviously, there's sea level change, okay? Because as we know, through things like thermal expansion, which is obviously water expanding under heat, a simplest term, but we also have, obviously, as ice sheets and glaciers melt, they were adding more water to that around the oceans, okay? So we're going to see that rise. So if we can see sea level rise happening, then it is further evidence that clearly that climate will be increasing in its temperature. So a nice, simple one. Again, you can see those ones that we mentioned about the freshwater ice is one key factor behind that, and that thermal expansion as a second one. So that concludes our recent evidence for that. But obviously, that's sort of looking at that very recent, but we can also look at, physical or natural changes behind climate. So not ones that we can see, and not one that we've caused. So what are those all about, sir?
Thank you, sir. So there are also, as Sir just said, natural changes that exist in our environment. And those natural changes are mainly because of what's above us and what's around us. So the Earth's natural cycle. There are three things you need to know about natural changes to the climate. So they are the Milankovitch cycles, sunspots, and volcanic eruptions. And I'm going to make this section really simple for you, because a lot of people and a lot of students get confused with the Milankovitch cycles. So essentially, the Milankovitch cycles are all about how the Earth orbits the sun. And there are three different aspects to how the Earth moves around the sun. There is eccentricity, obliquity, and precession. Now, eccentricity is all about the shape of the Earth's orbit. So the Earth can orbit the sun in a circular manner, and that would mean that there are no real changes. It wouldn't really impact the environment or temperatures that much if it just circled in an exact circle. Whereas if it was to change its shape to an oval shape, that would mean that the Earth is further away from the sun at some times a year and closer at others. And that then would mean that we could potentially see colder periods or warmer periods. Because remember, the closer the Earth is to the sun, the more solar radiation, therefore the more heat received by Earth. And the further away on that oval would mean the less solar radiation and therefore the less heat. So eccentricity is all about orbit. Then we have obliquity, and that is all about how the Earth tilts on its axis. So the Earth is on its axis, or on an axis between the North and South Pole. So if you thought about a big axis that links the North and South Pole together, and remember then I said that the Earth can tilt. If the Earth, for example, tilted slightly away from the sun, okay, what you would have is, let's say the South Pole is tilted towards the sun and the North Pole is tilted away from it. Now, what you would have there is the South Pole would be receiving more solar radiation, so it would be in daylight more, and it would also be warmer, or temperatures would rise. In the North Pole, in this case, what would happen is the North Pole would be in more darkness, it would be wintertime there, and temperatures would be on average lower than in the South Pole. So the Earth can tilt, and that is called obliquity, and that can affect temperatures right across the world, but particularly in the North and South Pole. And finally, precession. Now, precession is about the Earth's wobble. And actually, this one's the simplest of all three. So while the Earth is on its axis and while the Earth orbits around the sun, and whilst it also tilts, there is a slight bit of wobble taking place on its axis. So it's not a smooth surface, if you like. So what happens is, as the Earth orbits and as it tilts, there is a slight wobble to that axis. And as the Earth wobbles, therefore, and we don't notice it obviously, as it wobbles, it changes its distance to and from the sun slightly. And that changes the solar radiation coming to and from the sun as well and being received by Earth. Mr. Unite, would you have anything to add to the Milankovitch cycles there?
Oh, I think they're really good, sir. For me, it's just a few ways of trying to trigger their responses. So eccentricity, I've always sort of seen it as like a football versus a rugby ball for those shapes, you know, as simple ideas. And if you're eccentric, you're over the top, that sort of thing. Obliquity is tilt in it, if you did it as a little anagram as well. But I generally find my students struggle to remember precession. So yeah, got to find out a nice little rhyme for that, sir. But there we go. Well, I'll keep trying to work on that one for you. But obviously, there's other ones out there as well. So sunspot volcanic eruptions. What can you tell me about those, sir?
Yeah, so these ones are, these are really small parts of the course, so we can afford to here just be really simplistic in what we're saying. Sunspots are basically dark spots on the sun, okay? So these would be like little dark patches, dark circles. And what they do is they're almost like very intense patches of the sun. And they actually increase the amount of energy the Earth receives from the sun because they are very focused. And they essentially give more solar radiation to the Earth. So they actually increase the amount of energy that they are giving to Earth, which could therefore potentially increase temperatures. And then finally, volcanic eruptions. Now, these ones, of course, we know that volcanoes release a large amount of dust and gas when they erupt. Now, some major volcanoes, they can go on for a long period of time, and they can produce lots of these gases. Now, when they do this, what they can do in extreme cases is block out sunlight in certain areas of the world. Because of the amount of gas in the atmosphere, we can actually create a haze over the sun that blocks out sunlight. So it becomes dark, and that can happen for long periods. Now, when that happens, obviously the sun's rays can't get through that thick cloud of gases. And so actually the Earth cools because it's not receiving its solar radiation. However, Mr. Unite, what happens then in the long term? What can actually happen?
In terms of that time for volcanic eruptions in general?
Yeah, so what can happen to temperature in a long-term period then? After it cools because of the blanket of gases, when the blanket of gases disappears or goes into the atmosphere, what actually happens in the long term to temperature?
Well, eventually it'll return to normal. So back to sort of pre levels. And then obviously there's some good examples. I remember teaching before about the Tambora eruption, I think it was, around about 1815. And that was an entire summer where a year without a summer entirely. And there's also other examples where ships couldn't sail in other eruptions for like 8 months of the year. But yeah, it will dip for that certain while of time, and then eventually it will return to an adjudged normal.
Yeah, exactly. And you were just talking about examples there of how this can happen. And obviously, the Tambora one of 1815 is one of the most famous ones, isn't it? But
there's some great ones out there. If you watch YouTube, like biggest ever eruptions, there's some great stuff on there. Some scary stuff as well, though, sir. Some scary stuff.
Yeah, and if we even relate back to thinking about global hazards, ash clouds, of course, from a volcanic eruption can be seriously damaging to not only people's health, not only the environment, but the economy as well. If you think about the Eyjafjallajökull eruption back at the start in the 2010s, but that caused havoc, and I'm sure some of our students might remember it currently, or will know of it. That caused havoc for the economy of most of Europe because of airlines not being able to fly in ash clouds, etc. So yeah, there are some really good examples. You could just YouTube them, as Mr. Unite said there. There's some really good examples of volcanic eruptions and how they've changed the environment and the economy over time. Mr. Unite, would you like to talk about the greenhouse effect?
Yeah, I'd love to. You're going to keep this one really nice and simple because I'm sure you've probably done this plenty of times in middle school science as well. So the key thing for us as geographers is we have two different types of the greenhouse effect. We have one what's called the natural, and that is enhanced, okay? So in terms of the natural, we'll go back to those basic principles that the solar radiation of the sun reaches Earth, and obviously some of it will be reflected back into space. Okay, the idea that we know is that the greenhouse gases create, an invisible blanket, if you so want, that helps to trap some of that solar radiation. Therefore, acting a bit like a greenhouse where you'd grow your tomatoes, other fruit and vegetables are available, obviously, but that allow you to see life occur. Because as you can see in this little bit of knowledge here, it would be about minus 18 degrees if we didn't have that effect. So we do want to distinguish between that is the natural process, which is good and required for life, and that which is called the enhanced. The enhanced greenhouse effect is essentially where we keep adding to that blanket, as you so wish. And this is as a result of human contribution. Okay, so this will be us using gas, oil, coal, anything that emits greenhouse gases. All of those things will make the atmosphere thicker and as a result trap more solar radiation, resulting in a warming. And this is where, here's a similar graph to the one that you saw before. It's the same time period, but you can start to see that line is sort of almost like carbon dioxide increasing, how global temperature follows that. It's very closely aligned. So we can see that as we increase the amount of carbon dioxide that we have, there is that positive correlation, if you so want, with the actual global temperature. And again, we can see there's fluctuation there, but overall, we can see that general trend increases it. And that's what we call the enhanced greenhouse effect. So the natural is obviously the natural occurring one, good for life, not linked to global warming and humans. The enhanced is. Anything on that very quickly, sir, before I quickly run through greenhouse gases?
No, I wouldn't add anything to that. Nice and simple there. Just remember, natural is the environment doing its own thing. Enhanced is we're adding to it. Simple as that.
Yeah, like that. Yeah, perfect. So nice and clear. So again, in terms of greenhouse gases, again, I'm sure you know some of these that you probably use. Carbon dioxide is always one that we draw upon, okay? It comes up in so many different uses, including things like in sustaining ecosystems, where we talk about carbon sinks and stuff like that. So all you need to know is, have some good knowledge about recognizing greenhouse gases. So if there's multiple choice questions, identify greenhouse gases, or can you give us, 2 examples of them? Well, we've obviously got carbon dioxide and methane. They would be 2 that I would say crop up the most. So carbon dioxide is obviously the most significant, the one we know about the most, providing about 60% of all enhanced greenhouse gases. It comes from our production of electricity, your cars, and obviously as we destroy the rainforest and their ability to hold on, like a sink holds on to water, they don't act as carbon sinks any longer. So therefore, we find that carbon isn't trapped in those trees anymore, but is available to create that thicker blanket. Methane comes up quite a lot as well, because we talk about cows and obviously their emissions of methane as well. And again, we could link that to the increase in deforestation in places like Brazil, where we turn that land from forest to obviously grazing land for agriculture, increasing the amount of methane that we need. But what's important here is it can come from other sources as well. So you might be given some pictures, you could be given a landfill, there might be a picture of an animal, and you go, oh, well, cows create global warming. Well, it's not asking that, it's asking for you to identify that from those cows or other farm animals that we're looking at methane. Okay, there are 2 others. Again, I'll skip through because these are probably the 2 that you will least know about, the ones that we don't use across the course. So we can look at halocarbons, which are basically human-made. You might find them in things like refrigerators and stuff like that. And again, they are extremely dangerous, but they make up an absolute, it says tiny there, it should be tiny proportion of greenhouse gases. But it is a significant factor in trapping more. But it is so minor. Maybe go away, find out the exact amount if you want to whilst we're looking at it. Nitrous oxide, again, as you can see, is about 6% of all of them, but it's 250 times more efficient than carbon dioxide. And again, that generally comes from things like fertilizers and car exhausts. So just make sure you're really confident identifying those, but realistically, carbon dioxide and methane are the ones that we really want to draw upon because they're synoptic, or they appear in other pieces of our course as well. So last but not least, we want to think about, where do these come from? Who's to blame? Who's responsible for these greenhouse gases and that enhanced greenhouse gas effect? Mr. Hatchell, who's to blame?
Thank you very much. I'm certainly not. I'm joking. So
very nice.
We do this in A level as well, in A level geography, and there's some really key things to remember here. Generally, the more developed a country is, the more responsible they become for greenhouse gases in the world atmosphere. Okay, so LIDCs, let's start with those. These are low-income developing countries. These are responsible for minimal greenhouse gases, and that's because they're not industrialized yet. So they are not manufacturing lots of different goods and items such as cars. So they're not consuming lots of energy either. Then we have our EDCs. Now, these are our emerging developing countries. These are actually very highly responsible. So countries like China and India, who are growing rapidly, massively expanding, building factories all over the place, so they can build and create more products for the world and export them around the world. These are very, very highly responsible for greenhouse gases. And you can see on the pie chart on the right there, for example, India and China are two major nations have ACs. Now, these are countries like the USA and the UK and so on. And these countries, and we know this, we enjoy wealthy lifestyles. We enjoy all of the goods that we want. We enjoy flash cars in some cases and so forth. All of these goods, even coffee machines, these produce greenhouse gases either in using them or manufacturing them. And they usually come from EDCs, don't they? We usually buy them from EDC countries. So these countries, ACs like the UK and the USA, also produce a very high amount of these greenhouse gases. And again, you can see on the pie chart on the right here, the USA emits nearly 20% of all of the world's greenhouse gases. You would think that because the USA is a very rich country, that it might have invested more in green energy and so on. But actually, they have a very abundant supply of oil and coal and so forth. So they are still using those older, more traditional energies because they're cheaper, because it's cheaper for the USA to do so. They are investing in green energy, but not as highly as they could be. Finally, just something to remember on carbon emissions. Yes, China is very, very responsible at 23% of all of the world's carbon emissions, but remember, China have 1.4 billion people in total living there, a 1.4 billion population total. All right. The USA only has around 320 million. So actually, as a per capita or per head, the USA is the largest polluting country in the world. Now, that is per capita if we break it down and divide it per total of the population. But still, both China and USA's carbon emissions are very high. Mr. Unite, anything to add?
No, really good, sir. I mean, I've definitely had some good discussions with some of my GCSE groups before where we talked about, EDCs do have that industrial and they think, oh, that's really significant. But we often forget that actually, because we are industrialised, we were in that same stage before, take back the Industrial Revolution in the UK, cutting down all the trees and all that production there. So it's always something to think about that, where we are now is almost a bit of a privileged position that we can try to choose, and we've got the technology or the ability to try and use those renewable sources, whereas other countries maybe don't necessarily have that ability to quite yet. But no, really good, sir. Really enjoyed that. That was good.
Right, brilliant. Well, that was part one of Changing Climate. Part two will mainly focus on the case studies of this topic, so it should be slightly shorter than this, actually. I hope you enjoyed this, and I hope you found it useful for your revision. And you can flick over now to part two of Changing Climate. Thank you very much.